Hi students, Professor Nugent here. In this video, we're going to discuss confidence intervals for prediction two different ways. We're going to look at confidence intervals for prediction within sample, and we're going to look at confidence intervals for prediction out of sample. Let's start with confidence intervals for prediction within sample. So we have a prediction for y hat equals beta naught plus beta 1 hat x1 all the way through beta k hat xk, right? And it's natural to think about what a confidence interval may be for this prediction y hat. The tricky part is the standard error for that prediction is going to depend on a linear combination of the estimators. So what we can do is the following. Denote theta naught equals b beta naught plus beta 1 c1 through beta k ck. So this theta naught is the value of y for the value x1 equals c1, the value xk equals ck. Let's write that as such. This is equal to the expected value of y for x1 equals c1, xk equals ck. Great. Then we can rewrite this in terms of beta naught, so that beta naught is equal to theta naught minus beta 1 c1 minus beta k ck. And now what we can do is plug this into the regression equation. Y is equal to theta naught minus beta 1 c1 minus beta k ck plus beta 1 x1 plus beta k xk, and distribute out these terms, beta 1 c1 with beta 1 x1, and we have that this is equal to theta naught plus beta 1 times x1 minus c1 through beta k times xk minus ck. So what you can see here with this last line this is y. You run the regression of yi on x1i minus c1 xki minus ck. And then the predicted value for the intercept, theta naught, is that y hat that we were looking for. That's the expected value of y given x1 is equal to c1, xk is equal to ck. And the standard error can be used for the confidence interval as usual. Good. So this is within sample, and this is going to give us a prediction for the average value of y for the subpopulation that has these values for their covariates. But you may ask, what about a prediction for a unit like a firm or a school district or a county, a house, that is out of sample. So this may be a value y0 that we want to predict that's equal to beta naught plus beta 1 x1 0 through beta k xk 0 plus u 0, where the x1 0 through xk 0 represent the new values for the independent variables. Good. So the best prediction is going to be with the OLS regression line. The resulting prediction error, the prediction error is E0 hat, which is equal to y0 minus y0 hat, which is equal to beta naught plus beta 1 x1 0 through beta k xk 0 plus u 0 minus y hat 0, right? So y0 is equal to this plus this, y hat. And we want to show that the expected value of E0 hat is equal to the expected value of this, expected value of this whole thing, right? We can put this whole thing in the expected value. Now, the betas are the population parameters. The x's we treat as fixed and repeated samples. So then all of this comes out of the expected value. And we are left with beta naught plus beta 1 x1 0 through beta k xk 0 plus expected value of u 0 minus y hat 0. Oh, we want to take the expected value of that. And expected value of u0 is 0. Expected mean of the residual is 0, right? Expected value of y hat 0 is going to be this, right? Beta naught plus beta 1 times x1 0 through beta k times xk 0. So what you have is beta naught plus beta 1 x1 0 plus beta k xk 0 minus beta naught minus beta 1 x1 0 minus beta k xk 0. So this whole thing is equal to 0, and we have shown that the expected value of the prediction error is 0. Good. So the best prediction is with the OLS line, and the resulting expected value of the prediction error is 0. Let's think about the variance of this thing. What is the variance? And the variance is going to help us with the confidence interval for this out of sample prediction. So the variance of E naught hat is equal to the variance of the whole thing, right? Y naught minus y naught hat, which is equal to, so the betas and the x's, they don't vary. The betas are population parameter, the x's are fixed and repeated samples. So they're not random variables. So we're left with, so they all drop out of the variance expression. We're left with u naught minus y hat, oh, that's not, u0 minus y hat 0, which is equal to the variance of u0 plus variance of y hat 0 plus 2 times the covariance of u0 y hat 0 by virtue of the characteristics of variance. Okay? Now we know that the covariance between u0 and y hat 0 is 0, right? Because y hat is a linear combination of the x's, and we have assumed that the by the zero conditional mean assumption, zero conditional mean independence assumption, things are independent. So the covariance, this thing is 0. So we're left with variance of u plus variance of y hat, which is equal to variance of y0 hat plus sigma squared, because that's the variance of u. And we can estimate the variance of y0 hat in the usual way. We can represent the standard error of E0 hat as equal to the square root of the variance of Y0 hat plus sigma squared hat. And so the 95% confidence interval for the out-of-sample prediction is going to be given by Y0 hat plus or minus t.025 times the standard error of E0 hat. Now observe that the standard error of this thing is going to decrease with n because the variance of Y0 hat decreases with n, but the error variance does not. So the error variance may dominate this term, especially if you have a low r squared. So if you have a low r squared, then you're going to have a high error variance and therefore a high standard error, and prediction is going to be very hard because you're going to have a very large margin of error, a very wide confidence interval. We can use the student's t-distribution, observe because the betas, we have assumed the betas are normally distributed. So y hat's normally distributed, and we have assumed that u is normally distributed, so if these two things are normally distributed, then this thing is normally distributed. All right, so we can use the student's t-distribution. All right, so that's it for the confidence intervals, 2 ways. Stay tuned to the next video. We will discuss predicting y when the log of y is the dependent variable.